That is gonna be problem session for chapter 3. Let me consider problem 25 on page 56. In this problem, we have a set L of all positive integers. And we have operations on the set defined as follows: A plus so-called B is the product AB. So A and B are two positive real numbers. Their sum in a circle is defined as their product as positive real numbers. And also we define the product operation as A taken to the power log B. I should say I consider log as natural log, so log B, sometimes and frequently denoted ln B, is the same thing as log E. B and E, as you know, as 2, 7, 1, 8, so further. So if in the book the base for the log is not specified, if it is not E but something else, the changes are small, not substantial in this problem. So in the first place, I want to a little bit discuss this product. It looks very non-symmetric. And I will say that this product, in fact, is symmetric. So we say A to the power log B, this is same thing as A is, in particular, with this, where no A is exponent of log A. With other base, we have to write something else here, but we assume this all logs are natural. E to the log A taken to the power log B, which is the exponent of the product of logs, log A times log B. And now it looks much better than this one. It is symmetric in A and B. From this symmetric form, because this is just a product of two real numbers, log A and log B, we immediately conclude that F, this is a ring if L with these operations is a ring, then this ring is commutative. A times in circle B is equal to B times in circle A. This is axiom 9 from our lengthy definition of what is a ring, what is a commutative ring, and so further. Now, however, the question is whether this is a ring at all. There is a bunch of questions in this exercise. So they ask whether this is a ring, whether this is a commutative ring, and finally, I believe, or just a moment, I will double check how do they ask that. First of all, this is problem not 25, but 26. I'm sorry, I have a double check. 25 is very similar, but not this one. This is 26. And they ask whether it is a ring, whether it is a commutative ring, and finally they ask whether it is a field. So basically, all these problems are very lengthy. You really have to check ring axioms. At the very end, I will show you a shortcut. But now let us go in a straightforward way, checking the ring axioms. As it is supposed to be done in this section, in section 3.1. Well, it is lengthy but straightforward. So we have to check closure and associativity. They are clear. These are 1, 2, 6, and 7 from the list of the axioms, and 7 from the list are clear, straightforward. Now, indeed, let me comment just about closure. Point is that the sum of this so-called the sum of two positive real numbers will be again a positive real number. This so-called sum is a product, so product of two positive real numbers is indeed a positive real number. So addition is closed. What about multiplication? We take two positive real numbers. We want to make sure this number is again a positive real number. Oh, I don't know about whether for you it is convenient for powers of a, whatever it is, when a is not something rational. But anyway, you may think, oh, the power is not rational, but you may think about exponential here this way, and of course exponential immediately takes all positive real values. So all values of exponential are positive reals. So if we take a and b positive reals, the logarithms are defined. Whatever the product is, positive, negative, does not matter. Exponential of any real number is a positive real number. So indeed, this suspected ring, the set L, is closed with respect to this operation of multiplication. Associativity comes, 6 and 7, comes from associativity of multiplication and multiplication of logs. So all straightforward, you write this operation and the multiplication better in this form. You check the closure and associativity. Commutativity for addition. Addition must be commutative. This is commutativity for multiplication, which may be or maybe not. If it is here, if it is around, then the ring is called commutative. For addition, everything must be commutative by definition of the ring, and commutativity this is free in the list of ring requisites, and this is implied by the commutativity of, no, look, whether b plus a with this O plus is equal to a plus b. Yes, of course, because the products a, b, and b, a of real numbers are the same, so it is implied by the commutativity of multiplication of real numbers. Zero, what is 0? Axiom 4 for the ring requires the existence of special element 0. So 0 in this ring, so this is about 4. 0 in L is going to be the number 1. So real number 1, positive real number 1. Oh, indeed, A, whatever positive real A is, this is by definition A times 1 as real numbers, and this is of course A. So for every real number, A plus 1 or 1 plus A, doesn't matter, 3 already proved, is equal to A. So real number 1 plays the role of 0 in this ring. Now we have to convince ourselves that linear equations are solvable. This is going to be 5. We want to solve linear equation a plus x equals 0. So this equation should have a solution, element negative a, and this is plus in circle, for every a in L in our set. Oh, you can easily check from this multiplication formula that the element negative a is simply the real number 1 over a for positive a. This is of course a positive real number, and 1 over a times a is 1, which plays the role of 0. Now we're going to check distributive law. That's 8 in the list of axioms, distributive law. From the list of axioms, 8. Now, what do we want to see? We consider A times B plus C, and we want to see that this is A times in circle B plus A times in circle B, C, and plus is also circled. Let us see what happens. So A, B, C are any positive real numbers. So this is A in circle, but this thing, B plus C, by definition, this is the product of two reals. So this is simply BC. And this is equal to, now I will write it this way, e to the log a. This is still a. I want to multiply, and multiplication is here something or times in circle something is e to the log this times e to the log this. I rewrite this formula. So now multiplication is here, and normal, not times e to the log, but log times log. This multiplication is normal multiplication of numbers, not necessarily positive. In fact, logarithm of positive number may be negative if the number was smaller than 1. But still, this is normal multiplication of numbers. And now we use the well-known property of log, that this is e to the power log a, and we write log of the product as sum of logs. Now the distributive law works here, and that is how it will work. That is the reason why it works, in fact, for in this situation. So this is e to the power log a times log b plus log a times log c. Now I can use the property of exponential, e to the log a times log b multiplied by e to the log a log c. What I see here, this is a product in our ring. This is how the product was defined with this formula. And so I will write it. So this is a product in the ring B, and this becomes plus product of two real numbers as sum in the circle of this one and that one. So this is A times C. We're done. So we found that A times B plus C is A times B plus A times C. So distributive law 8 is satisfied. Since we know already that if it is a ring, it is commutative, we can skip doing everything twice from left and from right. So far, we found that what we have is, so we can conclude here, L is a commutative ring. So again, what did I do? I checked the operations not in the order 1, 2, 3, in the order which was more convenient for me. For example, I started with commutativity so that I spared left and right double checks. After that, I checked them by groups as I introduced them. Possibly it is a little bit more convenient to do that. Or if you cannot guess who was the zero, you have to first think how to make the product the same. So this is 1, so who is 1? This must be number 1, must play the role of 0. So this was kind of guess. I told you this is going to be the 0, but it is actually easy to find. So altogether, this is just a straightforward check that all requirements are satisfied. Now we'll go further and check that this ring has identity. the role of identity in L is going to be played by e, the base of logarithms. Oh, indeed, a for any a times this number e, this is a positive real number, which is going to be to play the role of identity. Now I want to justify, yes, this number does play the role of identity. By the definition of this multiplication in circle, this is going to be e to the log a times log a by our modified definition. I started with modifying the definition. It looked awkward. I wanted to make it more symmetric. Now, what is log a? Log a is 1. This is 1, so log a times 1 is log a. E to the log a is a, which means that indeed the number a plays the role of identity in this ring. So we know that this is commutative ring with identity. Is it an integral domain? Let us try that. Oh, integral domain requires that identity is not 0 in the ring. Yeah, it is the case here. Identity in L, as we found, is the number e plays this role, and this is not equal to 1, it's bigger than 2, which plays the role of 0. The requisite property of integral domain is the product is 0 implies one of the factors must be 0. So let us see whether that is true. Assume a product B is 0 in L, and let us rewrite it. What does this mean? This means that e to the power log a times log b is 1. This is the 0 in L as number 1. E to something is equal to 1 implies that something product of logs is 0. Log a times log b is 0. Now it is not 0 in L, this is number 0. 0 in L is number 1. Now the product of two numbers is 0 implies one of these numbers is 0. So this log a and log b are nothing but two real numbers. So I have log a is 0 or log b is 0. Log a is 0 happens when a is 1, which is 0L, 0 in the ring L, or B is 1. Log is 0 when B is 1. So what I found, if this happens, if the product in circle of A and B is 0 in the ring, then either A is 0 in the ring or B is 0 in the ring. Then indeed, yes, integral domain yes, L is an integral domain or in other words, 11 is satisfied. Last step, maybe it is a field. The answer is yes, it is a field. And this is about 12, which is also satisfied. Meaning the equation, I'll justify it for you, the equation a times x equals 1 in L can be easily solved. Is solved by, has a solution, x is exponential of 1 over log a. So, we can, for any positive a, so if a is, log a is not 0, because a is not 0 in L. So, it's solved by this x, log a is not 0, because a is not 0 in L, otherwise we don't want to solve this equation. So we solve this equation one with non-zero a's, meaning a is not 1. Here is a solution. You can easily check that this is indeed a solution to this equation. So for every a except 0, this equation has a solution. This equation has this solution. So yes, we found finally that L, this set of positive integers denoted by L in this case, is indeed a field with these operations. Now, what we did was a very straightforward check of all axioms. We found that this is a ring. After that, we checked all requisite properties to find that this ring is eventually filled. Another way to approach this problem, this way which I just showed you, comes from section 3.1. Now, I will show you how you can approach this same problem from the point of view of section 3.3. So, same problem. Same exercise from the point of view of section 3.3. This is going to be a problem similar, an exercise similar to exercises 20, 21, 22, 23 on pages 81, 82. I will not show you how to solve these exercises. Instead, I will continue that same problem and show you how to do that. So what I want to say that the field L which we just discussed is isomorphic to the field R of all real numbers. Moreover, as soon as we get that, we will not need to prove that L is actually a field. Besides, whatever it is, a ring, commutative ring, whatever, we will immediately prove that L with these operations is a field isomorphic to the field of real numbers. And that kind of illustrates both an alternative approach to that exercise, how you may do that without going annoyingly through all axioms. At the same time, this is an illustration what isomorphism is about. So, a solution to that problem would be reformulation of this statement that L with these operations. So, what I want to show a reformulation L with the operations defined above is isomorphic to the field R of real numbers. To start with, isomorphism is always a one-to-one map. So let us construct a map from all real numbers to L, which is the set of positive real numbers. That is very easy. You probably know a very natural map which takes any number x and maps it to exponential of x. That map is nothing but exponentiation. This is a one-to-one map of sets. Indeed, you know that the map, first of all, this is indeed a map. Any exponential of any real number is a positive real number. You know probably from calculus. You also know that the map is injective and surjective. Surjective because we have an inverse, or injective for the same reason. We have an inverse. We have logarithm. So the logarithm is V inverse. Soon as we have one map and its inverse, so we go back and forth, we have a one-to-one correspondence between the two sets. So to every element, to every real number, we have a positive real number. To every positive real number, we get a real number. course, negative numbers map to something smaller than 1, positive numbers map to something bigger than 1, and 0, e to the 0 is 1. Now let us see what this map does with operations. Real numbers have operations. These are addition and multiplication of real numbers. You know about them. Now think about this one-to-one correspondence, kind of relabeling elements of R. Instead of x, you write e to the x. You label elements of R with elements of L. You add two elements of R. What happens with the corresponding elements of L? Not corresponding, these are the same. How they add together what corresponds to the operation of addition. In other words, I want to make this map a ring homomorphism. Then it's going to be isomorphism because it is one-to-one. I want to make a ring homomorphism out of that by brute force. Just I take the operations here and define operations on L in a way such that this map is a homomorphism. So it must take sum to the sum. Let us see how it works. We take a sum of two real numbers, x plus y, and map that to exponent of x plus y, which is, of course, exponent of x times exponent of y, which is the addition here. The elements here are labeled by e to the x. This is the operation of addition. So this is e to the x plus e to the y. This is where sum is taken, to sum. So we relabeled real numbers with this symbol e to the x. Then the sum becomes the product of two real numbers. You see? How does it work? And what about the product of two real numbers? Maps to e to the xy with this map. So this real number is labeled this way. And I will rewrite it. I want to rewrite this real number in terms of e to the x and e to the y, because these are the labels, as I easily wrote this number corresponding to sum in terms of labels, e to the x, e to the y. Now here I write that this is e to the log e to the x, this is x, times log e to the y, this is y, which is now, by our definition, or other ways we define the multiplication, as multiplication, usual multiplication of real numbers with these new labels for them. So this is e to the x, e to the y. That's all, we are done. With that, we got L in one-to-one correspondence with real numbers. And the structures, addition and multiplication operations on L, just coming from the corresponding operations on real numbers. So we simply relabeled and look how the operations look like with this relabeling. Instead of x, we write e to the x, and look how the addition x plus y looks like. This is how it looks like. Similarly, multiplication looks this way. If instead of x and y, we want to write e to the x and e to the y. That's all. So actually what we proved that L with these operations is isomorphic to the field of real numbers. This is a proposition. Now I may say that this is a proposition, and this is the proof of this proposition. That's all for the proof. So there are two ways to interpret this argument. One way, we simply introduce the operations on L according to relabeling. Another way to say that same thing, let the operations be introduced, and we check now that sum with this maps to the sum in L. Product after this maps to this product in L. So that is all. So first of all, we proved that the field L is isomorphic to R, and therefore it is a field. So the L with these operations is isomorphic to a field of real numbers, therefore it is a field. And this way we do not need, we proved everything, it is a field, therefore it is a ring, commutative ring with identity whatever you want. A field has all these properties without really checking them. We know these properties are true for the field of real numbers. Somebody told us real numbers is among the first examples of fields. This argument shows us that because L is basically the same up to relabeling, L is also a field and has all these properties. We do not need, in this way, if we approach the problem in this way, we do not need to check the properties directly one after one. So this section 3.3 style of solving a problem coming from section 3.1 is probably more conceptual and less routine. Right? I will show you some more problems from section, mostly or exclusively from section 3.2 in the next fragment. Thank you for listening.